Have you ever wondered how massive online services, the big ones, manage to stay online and consistent 24/7? Behind the scenes of so many of them, there's this unsung hero, a critical piece of infrastructure that's basically the internet's master coordinator. So today, we're going to pull back the curtain on something called ZooKeeper. So let's get right to it. Imagine you're building a service that runs on, say, thousands of different servers. They all need to agree on things, right? Like, which one of them is the leader? What's the latest configuration? And hey, which servers are even still online? Now, if they all try to update this information at the same time, well, you get total chaos. So how on earth do you coordinate all of them?
So, here's the game plan for this explainer. We'll start with the kind of chaos that ZooKeeper was built to tame. Then, we'll get into its unique philosophy, unpack its simple but super powerful toolkit, see how those tools let you build some truly elegant solutions, and finally, we'll check if it can actually perform at internet scale.
All right, first things first. Before we can really appreciate ZooKeeper's solution, we have to understand the absolute nightmare that developers are up against when they build these huge distributed systems. Yeah, it really boils down to a few massive headaches. You've got to manage configuration, making sure every single machine has the right settings. You need to keep track of group membership just to know who's on the team and who's offline. You absolutely need leader election to decide who's in charge. And sometimes you need these things called mutually exclusive locks, which make sure only one process at a time can touch something really critical. Get any of this wrong, and your whole system can just, poof, fall over.
So, how do you solve all of those problems at once? Well, instead of building a separate, clunky service for each one, the creators of ZooKeeper did something different. They took a huge step back and came up with a whole new way of thinking about the problem.
Okay, so you've got two basic ways of tackling this. The old way, that was to give developers these very specific, heavy tools, like a complex system-wide lock. But that approach can be super slow and really rigid. ZooKeeper's idea, totally different. It provides a simple, flexible coordination kernel. Think of it like a basic toolkit. And then it empowers developers to build their own custom solutions right on top of it. And this quote right here, this gets to the absolute core of their idea. They deliberately avoided what are called blocking primitives. See, a blocking lock means if one slow client is holding it, every other client that needs it just has to sit there and wait. It creates a massive bottleneck. ZooKeeper's whole philosophy is to be wait-free, and that is just non-negotiable if you want real performance. Okay, so what's actually in this magical, flexible toolkit? Let's dive in. It really all comes down to three simple but brilliant concepts. First up, just picture a regular file system on your computer. Folders inside of folders with files in them. ZooKeeper gives all the servers a shared space that looks and feels exactly like that. This is the common ground, the single blueprint that everyone can see and agree upon. And in this system, the files and folders have a special name. They're called znodes. That's really all they are. They're the fundamental building blocks, little nodes of data that live in memory, hold a bit of info, like the name of the current leader, and they can have other znodes nested underneath them. Okay, now this is where it gets really, really clever. ZooKeeper has this special type of znode called an ephemeral node. A client creates one, and if that client crashes or just disconnects, ZooKeeper automatically deletes the znode. Poof, it's gone. Think about how perfect that is for tracking who's online. Each server just creates its own ephemeral node, and to see who's alive, you just look at which nodes are still there. It is so elegant. And the last piece of the toolkit is the watch. So instead of a client constantly bugging the system over and over again, hey, has the leader changed yet? How about now? Now? Which is super wasteful, by the way. It can just set a watch on that leader's znode. Then, when that znode gets updated, ZooKeeper sends a tiny, one-time notification. It's a super efficient, event-driven way to stay in the loop. And here's the key thing to understand. That watch notification is tiny. It doesn't send all the new data. It just pings the client and says, hey, that thing you were watching, it changed. It's then up to the client to go and fetch the new information. This design is what keeps everything so incredibly lightweight and fast. Okay, so we've got our Lego bricks, znodes, ephemeral nodes, and watches. Now, let's put them together and build something truly elegant. We're going to solve the complex problem of a distributed lock, but without causing a system-wide stampede. This recipe is it's beautiful. To get a lock, a client creates a special, sequential, and ephemeral znode. ZooKeeper gives it a unique number in order, like lock 001, lock 002, and so on. The client then checks the list.
Is its number the lowest? If it is, boom, it's got the lock. But if not, and this is the genius part, it doesn't watch the main lock folder. No, it only watches the Z node with the number directly before its own.
And the result of this? This is the real power of the design. When the client with lock 001 is done and its ephemeral node disappears, who gets notified? Only the client watching it, the one that created lock 002, not the dozens or hundreds of others waiting in line. You completely avoid the herd effect where everyone rushes for the lock at once. It's an incredibly elegant, efficient queue.
Okay, the design is elegant, for sure. It's smart, but the million-dollar question is it fast? Can it actually hold up under the crushing load of a major internet service? Let's look at the numbers.
Whoa, okay, check out the difference here. It is massive. For a system that's doing 100% writes, meaning every operation is changing data, a 5-server cluster handles about 18,000 operations per second. But for 100% reads, that number just skyrockets to 165,000 operations per second. So why?
Well, it all comes back to that brilliant design. A write operation has to be agreed upon by a majority of the servers to ensure consistency, and that takes a little bit of time. But a read operation? Any server can answer that from its own local copy of the data. No big system-wide meeting is required. And this means you can scale your read performance simply by adding more servers.
So what this really means is that for typical workloads, which are almost always dominated by reads, the performance is just phenomenal. Even a small 3-server cluster can achieve a peak throughput of over 87,000 operations per second. That's some serious speed.
So we've seen the problem, the philosophy, the tools, and the performance. What's the core lesson we should take away from all of this?
It's this. ZooKeeper's power comes from its simplicity. Instead of forcing a complex, one-size-fits-all solution, it provides a minimal, weight-free coordination kernel. It gives developers a few sharp, simple tools and trusts them to build what they need. And the result is systems that are incredibly fast, reliable, and scalable. And that leaves us with a final thought. ZooKeeper proved that for distributed coordination, providing a simple kernel was way better than providing complex, heavy-handed tools. It just makes you wonder, where else could this less is more philosophy be the key to solving our most complex technical challenges?